I'm trying to learn how to pronounce names and names to pronounce. Anyways, maybe you've already seen from the program that besides myself, we have one other speaker coming from outside of Madras. And normally I would introduce, and he spent also, by the way, time in Darmstadt where I was working, and I think several years. No? You were quite some time with a colleague, not with me. But he promised me he would do a self-introduction. And he has the first slide as a self-introduction. So in any case, we're really thankful that we could catch you for this short course. And he's going to talk, I think, about fundamentals of some optics, because it's our experience that most engineers don't learn anything about optics, and we're going to need some optics for the rest of the course. So this is a good introduction. All the best.
Thanks a lot, Professor Propia, for giving me an opportunity to come over here, and to Professor Arvind also. So we had around 5 years overlap in different floors in TU Darmstadt CSI building. But I was doing PhD, and we had some interactions, but it is 10 years back. Okay, so myself, Subramanyan Namboodiri, Bayernaport is the full name, is always problematic in the airport and while booking and all the things. And in Germany especially, like you know how to code. So German selected, Namboodiri is the. I think I can go a bit slow because of the last talk, right, Professor Topia?
Well, 45 minutes.
45 minutes, okay. Okay, so.
Attention span.
So then this is about me. I haven't included the Indian counterpart. So I did PhD in the Center of Smart Interfaces at Technical University of Darmstadt. Now the names changed. So then I continued there because we developed an optofluidics laboratory in Professor Stefan Hart's laboratory, and I continued there as postdoc for 1.5 years. Then I moved to Paris, École Normale Supérieure Paris, for 1 year postdoc. Then I joined in NIT Calicut as faculty. This is my academic voyage. And my son born in Germany, so I have a souvenir from Germany. So I'm always connected. So this is my young group, 4 years, 5 years old, with beautiful faces. And two already graduated, just recently awarded PhD, and we work on assembly, transport, and also I don't want to leave my optics, so I always stimulate liquids with light, optofluidics. So whoever interested, okay, definitely we can interact. So with that, basically, let us start what we want to discuss. It's like just to motivate you, why we need to understand the basics of optics. Because if you look at the microscope, there are a lot of components. We may not be designing a microscope, but we will be doing some parts if you are doing an experimental technique. So we need to know how they are working, how they are behaving. This is our aim. And also, this is the video I have taken from Professor Propia on atomization, and this video we have recorded in our lab, a particle add and drop upon impact, how particles get redistributed and goes to the center. So, with that motivation, let us start. I couldn't see the.
Yeah, it's good.
No, the pointer.
You have to turn on. I will show you. You have. I will show you. So we put on the laser pointer, and then it takes a minute, but then it should work. So if you push now the pointer, and then you should be able to move it. That takes a little. Keep it pushed. That's it.
Yeah. Bit slow in response, so it may take some time for me to adjust. Yeah. So the contents what we have finalized is, okay, we will start with some of the basics of ray optics, because when we think about a lens, a microscope, we definitely need to know some of the ray optics part. Then to get to the resolution, the fine details, we need to understand about the wave optics. Then some introduction about the cameras, and I will tell something about the polarization and the scattering to continue with the other topics in this course. Okay. So how we define light? Because it's the most fascinating thing in this world, right? We see each other, and but how we define light? Because we need to consider it in a very entirely different ways. Like sometimes we consider it as rays, sometimes we consider it as waves, sometimes we consider it as electromagnetic waves, sometimes we consider it as particles. Different scenarios to explain its behavior, right? Agree with me? Some feedback will be helpful. Okay, so we defined, and then the basic law of reflection and law of refraction I don't want to repeat, and we will start with the image formation. Okay. So how we see ourselves in a mirror? Like this is every day in the morning we look at the mirror, right? But how we see each other? How we see ourselves? This is actually the starting point, image formation by a flat mirror. Okay. So in all the slides I kept a figure so that to optics, we need to have a feel. Okay. So let us look at this figure. So we have an object here, and in an object we can say each point emits. Like it can be reflection, it can be scattering, it can be like luminescent also. Right? So these rays goes to the flat mirror and reflected back. There it satisfies the law of reflection. And what our imaging system, our aim, our eye or our brain does is like this collect these rays. You can see different rays goes to the and extend, and wherever the crossover point comes, it forms the image. This is what an imaging system is, a ray tracing. So this is what actually how the image is formed. Then we always see in India, like when we drive, all of us drive like object is closer than they appear, right? Because in the rear view mirror is a convex mirror, right? How it works. So let us start. We have an object and the rays are falling, and it's a curved surface and reflects back, and these two rays are collected by our eyes, right? And the brain forms an image. Actually the image is formed closer than the object, but it says object is closer than they appear. To understand that, let us solve a simple problem. Like a 4 cm tall light bulb is placed at 35 cm from a convex lens. Focal length is given, I am not reading it. And if you determine the image distance and the image size, we will understand what exactly happens. We will get an image of 1.02. That means it is demagnified. Even though it is forming closer, but it is demagnified a lot. What is the advantage? Demagnified. So we have to adjust accordingly, but it increases the field of view because we can see more area on the back side. That is why this convex mirror is preferred for rear view observations. Because we have to understand that it is demagnified image because our brain is always have some perception, right? If it is small, it is far, right? So that confusion happens, but we have a larger field of view. Okay. And ladies always know, like convex, concave mirror, they use it. I am not repeating the slides. Okay, now I go ahead with the lenses. Lens is actually, you have a redistribution of energy after lens, right? If you put a lens, a beautiful figure you can see. S is the source, and the diverging wavefront, let us take it as a point source. This is too problematic for me.
Maybe, or you can sit down and use the...
I think I will just use my finger, that will be better. So diverging beams and a perfect optical system, it converges, you can see how the wavefronts are reshaping and converges and diverges further, right? These are conjugate points. We will come back to the conjugate points and reshaping of wavefronts at a later stage, okay? So let us start with this image. To understand this one, I would recommend you to read Fermat's principle and optical path, because if you look this figure, the rays start from here and reaches here. All the rays reaches at the same time, okay, Fermat's principle. But when we look this figure, it appears that this ray travels more than the central ray, right? But for optics it is not true because we have to consider the refractive index. That is why the optical path comes into play. Because the central ray actually travels more time in the higher refractive region, so that it effectively don't need to travel physically more, because optical path is basically the multiplied by the refractive index. Okay, so then I request, I don't have time to really go to the Fermat's principle and explaining how the focusing happens for a lens, but I recommend you to do that. And this is what happens when a concave surface comes into play. Like a plane wave gets diverged, there it gets converged. What's the point? And a converging beam gets parallel depending on the focal length. Okay. And the focal length can be estimated using this expression. Yeah, so let us start with the thin lens. Okay, so we are all familiar with this 1 by S0, 1 by SI, SO plus 1 by SOI is equal to 1 by F, and the magnification, transverse magnification actually is yi, the height of the image divided by the height of the object, and correspondingly there is a longitudinal magnification also comes into play. Okay. And we can see this expression in different forms in terms of the radial curvature, focal length, so please keep a note of it. Okay. This we always use when we design an optical circuit, we call it optical circuit, we have to use this always to have a proper design. And these are the different combinations possible for a convex lens, like you can have R1 radius of curvature is greater than 0, R2 is radius of curvature less than 0, then for a planar convex R1 is infinity, is flat, and R2 is less than 0. It goes like that. Okay. This image is really helpful to understand what are the things I have already told. Okay. So let us start with the first one. In the first one we can see a parallel beam is falling on that lens, right? That means object is at the infinity. Okay. Then we get the exactly at the focus. So all the rays goes through the focus because these are paraxial. This is parallel beams comes into play. And when we move and place an object after 2f, the image is formed between f and 2f. What the point? And when we put it at 2f, exactly at 2f we get the image. So these are important when we design an optical circuit, optical design, because we should know where the images are formed, right? Because where the object lies, where the image should be formed, because there will be a series of lenses coming into play, right? We will discuss about the two lens combination after that. Okay? And after that you can see when you place exactly at the focal point, the principle of reversibility applicable, right? You get exactly the opposite, right? And intermediately this is actually the reverse of this one, right? These two. So we have to understand that. And when you put the object closer, that means closer than f, it gets diverging, right? It's getting virtual. Clear? So this is how a single lens behaves for objects placed at different distances. This is the fundamental thing we have to understand when we go for a combination of lenses. I hope it is clear, right? So then, this slide have very important information. When we have an intuition always that of a planar convex lens always focus, right? A convex lens always focus, right? It is not always true, because we always keep this lens in air, right? That is why it focuses. But if you place it in a medium having higher refractive index, it will act as a diverging lens. You can see it here. Effect of a kind of concave behavior, right? And this is true, we have seen if you put an air bubble and you shine laser, it will diverge because the refractive index is less for air bubble, right? Inside it is air, outside is the liquid, right? So it will diverge. So we have to be careful where we place the lens. These are immersion systems. We do work on such scenarios also. Okay? So then let us try to combine, because till now we were discussing about single lenses, right? Let us put them together. In this scenario, we put these lenses in such a way that the distance between these two lenses are shorter than their focal lengths. So there is no effective image is formed, right? Intermediate image is not formed, right? So look at this figure. At the moment, don't worry about the L2. At the moment, don't worry about the L2. And look at this rays 3, which actually goes through the focal point of the first lens, right? And the ray 1, which actually goes through the lens. These two rays will basically decide the image position, right? Right? Now what we are going to do is we put the second lens, L2. When we place L2, what happens? L2 sees this as a plane, right? That means it should go to the focus, right? Because now it is parallel to this lens, so it should go to the focal. That means this beam, after placing this, should go through the F2. Got the point? Now we have to draw one more image, one more line, that is line 4, which actually goes through the center of that lens, right? These two will effectively decide the image position once you put the second lens within the distance. Then image is formed actually closer, right? This is what I have drawn here. This is a single lens. After you put a lens closer, actually a converging happens, right? You converge this scenario, right? And if you put a concave actually, instead of concave, that is the minus, it will diverge. Got the point? So these are important when we work with optics. Because because ultimately our aim is to form an image, right? Proper image at the proper position, right? So for that we need to know how we can manipulate, how we can guide the light through the optical system. Got the point? Yeah. So this is basically, let us see how it works when we place them separated in such a way that the separation is higher than the sum of their focal lengths. Then you get a image. And the calculation we are not going, it's very easy to do that calculation. So now we have seen the difference where what happens when you place them together and planes. So the selection of the distance between the lens really matters, right? Not only about the distance with which you are working and the nature of the images also, right? You look at the nature of the images formed, right? If you are working with a circular Gaussian beam, it doesn't matter much. But if it is an image, it really matters. Okay? So these are two important, very important things in almost all setups. Because at a later stage we are going to discuss about the F number, numerical aperture and all the things. And we all work with the lasers, right? What is the typical beam diameter?
5 mm.
5 mm? 1 or 2 mm? Typically, 5 mm is too much. 1 mm or 1 to 2 maximum. Okay? And this is not always sufficient for us. We need to expand it. How we can design an expander? There are two ways to expand it. First geometry is called Keplerian design. What we do is here, you take a short focal length lens and a large focal length lens, and this is the expansion ratio, f2 by f1. Okay? And what you have to do is, you have to put them exactly at the distance f1 plus f2. f1 plus f2. If you increase this, this will converge. If you decrease this, this will diverge. Got the point? Important thing you have to note down is here the assumption is this beam is parallel. If this is not parallel, it won't work. And most of the time it is not always parallel. Then the advantage of this setup is to correct that collimation. So this setup can do magnification as well as correct the defect of the source you have. Got the point? And then another setup is Galilean. Here we use a negative and a positive lens. And here also the distance is f1 plus f2, but one is minus, so that effectively we get a compact setup. In addition, we don't have an intermediate focus. This is having advantage, this is having disadvantage also. Advantage is such that, okay, high power systems, okay, we prefer this one. But if this beam is having some defect, because beams have some defects, so we will come to that later, okay? And if you want to purify it, you need to have the intermediate focus. So depending on the, because this is what we always say, optics is a tool, you should know how to use it, where to use it. Okay? So depending on the scenario, depending on the space available, depending on what you are working, you can choose one of these. Effectively f2 by f1 will decide you the expansion ratio. This is a crucial element in almost all the setups you are going to work. We also will do in the lab tomorrow. Today I will set up, tomorrow we will see. Okay? And about the conjugate plane. The conjugate plane is very important in confocal microscopy also. In all microscopes, we have to understand the importance of conjugate planes. So let us start with an object placed at the focal point. Then what is going to happen? It will be a parallel beam outside, right? We don't need to worry. Then you push this slightly out of F, you are going to get the first image plane, right? And then you can use this image plane, this is the conjugate plane, for the second lens as an object, right? So you can make a cascade and you can reach. This basically you can visualize, if you want, we can visualize it as a microscope, okay? You put the sample here, this is your imaging part, this is your illumination part. Is clear? Then what is going to happen? We are going to get an image overlaid like this. That means this is your sample and this is your light source. You get an image overlaid, whether you want that or not. We don't want the image of the light source in the actual image, right? You get an image with the filament over it, whether you will take it or not. No, right? So we want to precisely adjust the illumination. This is very important. How many of you are worked with microscopes? Have you heard about the coiler illumination? No. We will see. Okay? So if you are not doing it properly, these are the things we face. Like, on the edges, we see something, apertures are not properly done. This is actually a diffused image of the filament itself. But you can correct it. This way is basically coiler illumination. Is the first thing we have to do in the microscope. Okay, let us slowly look into this figure. On the left side you can see a ray path. On the right side see a ray path. Both are simultaneously going through the system. Okay. On the left side, if you carefully observe, is called a conjugate field planes. Here it is in focus for the object. This is our sample, substrate. Okay. And this is in focus at the imaging plane also. That means this plane is actually focused to the image plane. That means we are going to get the image. Then at the same time, this path is actually starting from the light source, right? But wherever this light path is focused, it is diffused. Getting the point? Wherever this is focused, this is diffused. That means you are going to get a uniform illumination, background illumination. You take the final position also, it's completely diffused, right? So you will get the object perfectly imaged in a uniform background. This is called coiler illumination. This is really important to have a proper microscopy images. Otherwise, the thing is, sometimes we do grayscale image processing, intensity plot, all will plot. But if your imaging illumination is not proper, everything is gone. Okay. So then, what other point before going to the wave part, the other point we have to understand is about the aberrations. There are a lot of defects comes into play. First one is like a material problem is like chromatic aberration. That means the different wavelengths feel different refractive index, right? And they focus at the different planes, and that's called chromatic aberration. And similarly, spherical aberration comes into play. Astigmatism, we will quickly go through it. Okay. And what is chromatic aberration? I already told you the violet or the blue focus further than the red. So effectively, you lose the contrast, right? You use white light to image. You lose the contrast because basically the images are formed at different planes, right? And this can be solved. This can be solved using a achromatic doublet or separated doublet. I will include only the achromatic doublet. Here the important is you have to use two materials. I will tell you why we have to use two materials. The condition is omega is basically the dispersive power NB minus NR divided by n minus 1. What is n is basically the average refractive index which we usually take for green. You take the visible range, we take it for green. And this is for the second material. If you satisfy this condition, we can correct the chromatic aberration, but dispersive powers are always positive. So to satisfy the above condition, focal length should have opposite sign. That is why you need to have a convex and concave into play, and that should be well in contact. If air or some other liquid which is having different refractive index comes into play, you lose the game. Okay. Then if you use the same material, this combination would lead to an infinite focus. Now use, right, for us. Then this lens material should be different, and you have to adjust the focal length accordingly. So this is one way of correcting the chromatic aberration. Clear? There is another way, but I am not going into that. So then the other one is the spherical aberration, like different from the center of the object, center of the lens, depending on the lens, they go to different planes, right? So a confusion occurs, which we call circle of least confusion, and we select a region where it appears more focused. So to correct this one, you need to work on the curvature aspect. Okay. The other one is the astigmatism. What is astigmatism? All of you know, I hope, right? You take like this, and this part give to a lens, and this part focus to one plane, and this part goes to another plane. Got the point? Means effectively you get a kind of elliptical kind of information. If you give a circular one, you get a kind of elliptical information, elliptical intensity distribution there. So this is also a problematic scenario. It's called achromatic. So before going to the wave part, I want to introduce the numerical aperture, which basically will help us explaining the resolution and all the things. Numerical aperture is nothing how sharp you can bend the light. It's like, I have an object here, I look like this, right? That means I use very high numerical aperture. It's clear? And that camera is far for me, and I use less bending angle for that, right? I don't need to bend farther, right? And this property is basically called numerical aperture. And this will define will help us to define the resolution of a lens. Before going to the diffraction problem, I would like to introduce about the interference. Anyone can give me an example of interference pattern you have seen?
Young's double slit.
Yeah, complicated, but today morning also we have seen something easier. We used soap and all of us took a bath, right? Yes or no? So then we have, we may not have noticed it, but beautiful colors from the bubble, right? It's a thin film interference. Because bubble is basically a liquid film, inside air, outside air, right? And the reflection from the top surface and bottom surface dance together to get the pattern. It's very beautiful. And also you might have seen color is continuously changing. It could be due to its moving, it could be due to its thickness is changing because of the evaporation. Angle of illumination, angle of observation is changing. And if just before the breakage, no color. That also I hope all of you have noticed, right? Please have a look at the physics into it. Here what I want to tell you is like, we have two waves, plane waves, represented in this way with the phase factor superimposed at this plane. Okay? The electric field is added like this, but the radiation intensity cannot be added like that. To have a better understanding about that, let us do a thought experiment. You take a laser beam, you take a screen with, not the screen, a sheet with two holes. Okay? Let these holes be close each other. And close one hole and see the screen. There will be a pattern, right? And now you close the first hole and allow the second hole. There will be a pattern, right? Then if it is just an addition, we should get something like this, right? Agree with me or not? First one is like this, second one is like this. I should get something like this, right? But when I open both together, I get an entirely different pattern, right? Yes or no? That is the Young's double slit experiment we say, right? This is because of this term, interference term, and set time varying function. Okay? And this is actually the effective path difference, phase difference, coming from the path difference as well as the phases of the individual waves. And this is a beautiful term we always use in interferometry. I is equal, the resultant is I1 plus I2 plus 2 root I1 I2 into that factor. Okay? And the maximum we get when this part, this is 1, and the minimum we get when this goes to minus 1. Got the point? And the fringe pattern will appear like that. The top is basically I max equal to I1 plus I2 plus root 2 root I1 plus I2, and the other one is the counterpart. And when both the beams have the same intensity, because we have a visibility factor, it's called a fringe visibility. It's defined as I max minus I min divided by max plus I min. This is very important. If you have a very strong beam and if you have a very weak beam, if you interfere, we will not see the interference pattern. Because the strength of the strong beam is sufficiently high to overlook all the patterns formed, right? So you need to have a kind of, understanding about what should be the intensity of these beams. If they are perfect, you get the 0 as well as 4I0 as the maximum. You get a perfect fringe distribution. Is it clear? Because the message what we have to take is like, when we do an experiment, we have to take care of all these things. Because we know when we put two laser beams split into two and put it to a same place, interference should happen, right? But many students won't see the fringes because of these kind of practical aspects they are not taking into account. Clear? Because I am handling optics lab in my institute, so I know it very well how the students take it. Okay. So now let us go to the diffraction problem. This is a beautiful pattern formed from a circular slit. Actually, I had a microstructured fringe to show different diffraction pattern, but the wall is not good for showing the pattern. So we will set up in the lab. Okay. So believe me, this is how the diffraction from a circular slit looks like. Okay. And if you look at the three-dimensional behavior, the central point, central maxima is actually having the maximum light, around 90% goes there, right? But for us, the first minima comes into play, right? It's very important for us, right? Because this actually, if you take a rectangular, this will be having a kind of rectangular information with the fading, bit of fading. Why the fading happens? Because of the diffraction effect. And the central part actually defines, somehow connects to the shape of the aperture we use for the diffraction. Okay, here is circular pattern, we get a circular. If it is slit, we get a similar pattern. Okay. And the first minima is very important for us because that will define our resolution condition. Okay, the first minima we get when this factor goes to 3.832, we have seen this one, and then we get angular resolution as 1.22 lambda by d. We are approaching. Okay, now we have seen a lens, an aperture, right? And we can consider it as it's applicable to a lens as well, right? Students don't believe it initially, but we can. I can explain. Okay, so you take a lens and put an aperture very close to the lens with matching to the diameter of the lens, right? We will get a similar pattern and this lens will focus this pattern, right? And you get a beautiful intensity distribution at the focal plane, right? And if you remove this aperture also, the same pattern we will get. Because the bending of light happens there also, right? Even without the aperture, because you have a clear phase boundary, right? You have a bending and all these beams goes through the similar region. These are waves and they interfere and get a pattern, right? So similar pattern or similar physics is applicable to the focusing of a lens as well. So what is actually the difference now? In the previous ray optics scenarios, we have drawn a crossover like this, right? Focal point, the rays crossover, right? That means an infinitesimally small point, right? It never happens because it's wave, so the lowest it can go is of the order of wavelength. So a bit of quantum mechanics uncertainty principle I have to tell, but I am not going to that. Okay? So this is how we define the resolution. You take two points S1 and S2, and this is the imaging plane. You have a corresponding iris patterns forms, right? And now you put this closer and closer, and your imaging plane will look like this, right? You are going to get iris patterns like this, and here it is overlapped. This is unresolved. This is the Rayleigh criterion. This is one standard technique to define resolution. The definition is like this, the maxima of the first one coincide with the first minima of the second one. Then the resultant intensity, because the individual intensity pattern distribution is like this, and the resultant intensity distribution will be like this, we will be able to separate the maxima points. So this is the condition for resolution. And we have to do a bit of some other adjustment. We have to rewrite in terms of numerical aperture, basically f by d. Okay? So then we will get the spot size at the focal point as a function of the numerical aperture. We have defined numerical aperture previously, right? It is the power of a lens to bend the light, right? So resolution is 0.61 lambda by Na. If you increase the numerical aperture, you get better resolution. But you cannot cross this, right? Lambda by 2 is the cutoff we have, right? And similarly, since it is an addition of waves, we have an axial component as well, not only the lateral component. So effectively you get a focal volume, not the focal spot. It's clear? And these expressions are really important for microscopy or So effectively you will see, this is the focal point, and if you demagnify and magnify, go down and go up with the microscope from the focus, you will see such patterns, and this is how effectively you can visualize the focal volume. And this slide is very important. This tells you the dependence of the numerical aperture on the image formation. We have seen how sharp the iris pattern, the sharpness of the object will be increased, right? So you see the different lenses having different numerical apertures, right? And here the same lens having 3 different numerical apertures, right? Because the filling is complete, then the full effective cone angle is utilized. This is also very important when we work with an optic system. We should know what is actually the back aperture of the final lens. And the magnification of the beam, we should define to fill that. Otherwise, even though you have a lens having a numerical aperture of 1.4, if your beam size is less, you are not going to utilize that completely. So these are the practical factors we have to really take into account when we design or when we work with that. Okay? This is very important. 2 types of objectives are there. If you look this figure, we are actually, our aim is to collect the information from here, okay, from this point, and here we are actually losing some information, right? Even though this lens is having huge numerical aperture, effectively only very few or a portion of the numerical aperture only we can exploit, right? Then, but if you fill in, that means if you fill this gap with a oil having similar refractive index of this cover slip, this is called oil immersion objectives, or water immersion objectives also will work. We can effectively utilize the maximum numerical apertures. So in microscope, high magnification, high numerical aperture imaging purposes, we use immersion, oil immersion objective lens. Is clear? The importance of this, why we go for this is clear? Yeah. This actually I did 2 days back to show you the spatial filtering. So we have seen the importance of the point, right? We have seen how the iris pattern looks like at the focal point, right? And this is actually a laser beam having, laser beam or some of the optics having some defect. You can see some fringes already overlaid, right? This is not the fringe I want to have it in my setup, okay? But it is there. I want to get rid of this. What I can do is, you use a lens and focus and design the pinhole in such a way that we have that 1.22 lambda f by d, right? We have that calculation, right? And design a pinhole and put exactly at the focal point. Then only the central component will go through. You see the difference? Because I was working on optical trapping in TU Darmstadt, so this was really a part of the game. You can clearly see the differences. We call it purified Gaussian beam. And this spatial filtering is an image processing display. Okay, so then another important thing is basically the depth of field. Depth of field is basically defined as basically the points, the range of the points with which you can see the object in sharper. Okay, so we have the expression. I think some error is there. I will look into that expression, what actually went wrong, but I will look into that, don't worry. Here basically the numerical aperture, magnification, all comes into play, and we have some final expression, but this is not always true because of the aberrations of the system. But we will get something close to this, okay? So this is very important. I should have put some photos, right? You all know about macro and landscape photography, right? And how the images looks like and what are the properties. I give you as an assignment, okay? How macro and landscape, what are the settings to get a macro photograph and a landscape photograph, okay? Then I go a bit on the camera aspect. I took the slides from Prosotropia because we have seen the fundamentals now. Now some introduction to the high-speed cameras. I don't have much to say here, but to show and share the slides. High-speed camera, you can see, you can even go to more than 1 lakh frame per second based on some models, but then the resolution you have to compromise because of the speed and all that. Okay? And this is different models, which I think it will be better to share so that they can go through it, and the cost, increases with the frame rate. So we have to be careful about where we want to work, okay? So then high resolution, sometimes we want, okay, that was basically high frame rate, right? 1 lakh frame per second. Here we need to have a more resolution. We want to see more resolution. We want to, so that pixel resolution should be very high, right? How the CCD is grown. Okay? So for that basically you have different models. Then you have the long working distance microscopes, what we have seen, because sometimes the field of view, working distance is not always easy to work with, right? If you take a microscope, you have very less working distance, and the field of view is also a problem. So telecentric approach, telescopic lenses are lens combinations are used. Here the advantage is, okay, you have a fixed magnification, decent magnification you will get, but you will have a good field of view and a reasonable resolution. Okay, and that highly depends on which objective lens you work on. And I have seen recently that an USB microscope, the normal USB microscope, can even go to 100x, 150x with a large working distance and a decent field of view. So the technology is evolving like anything nowadays. But what we have to decide is which one we want to. So then, before completing or finalizing this one, I will just go through the polarization and the scattering to have a continuity to Prosotropia's talk. So we have, I think I forgot the interference. Basically the basic criteria is like, you should have a good coherence and also a parallel polarization as well. What is actually the polarization? Anyone?
The light particle vibrate in the same plane of the light.
Yes, it basically tells you the orientation, right? It tells you how the electromagnetic waves are produced. Anyone? You take an electric charge. It is associated with an electric field, right? you oscillate it up and down. It's a moving charge now, right? It will produce a current, right? Current is associated with the magnetic field, right? Yes or no? So we have a charge and you oscillate up and down. Depending on that, you have an electric field, varying electric field, and a corresponding varying magnetic field is produced, right? This is how an electromagnetic wave can be easily produced. This is the same reason we don't need the source once the EM wave is produced. That is why we can see light from distant galaxies. Sometimes the galaxy may not be existing now. Till it get absorbed, because of this counter varying electric field, varying magnetic field, they will produce and they will continue till it get eaten up by some material, right? That is why we can see the history, our history from somewhere else. Okay, so then one photograph, I hope it will motivate you to work or to understand better about the polarization. The same frog, same camera, but a polarizer with a tilt, with a rotation. This one we prefer, right? So I don't want to go into the details of the polarization, but if you have an unpolarized light, it's like, incandescent lamp, this one is all different atoms emits different directions and we get all possible orientations, okay? So it's called unpolarized light. And when it goes through a slit, here we schematically draw a slit. This can be different materials. This will filter out certain vibrations, certain components it will filter out, and you will get certain orientations pass through it. Got the point? This is how we produce linearly polarized light. And there is elliptically and circular. This is already the mathematical representation of a linearly polarized light. Okay. So similarly, what you can do is circularly or elliptically also you can produce. How you can do? You take a charge, basically, you have to take it. So the helically, basically, the appearance basically will be helical, and if you take the cross section, it is circular. Okay, and the representation will look like this. You have a x and y component, and if you have x square plus y square equal to a square, that is symmetry. Then a phase difference pi by 2 between these components, you get a circularly polarized light. Usually we have to take some really into the details, otherwise I am really saying compressed manner this polarization, so I feel a bit guilty, but and this is how actually we make use polarizers in real scenarios. Like we have an unpolarized light, you put the first polarizer, and this we call analyzer. Okay, if you put a parallel to the first one, the whole intensity goes out, and depending on the angle, using the Malus law, I should have put that law here, and if you cross it, the light can be blocked. So depending on the polarizer, angle of polarizer, you can control the output intensity. And the final part, just starting to the scattering to have the continuity. So we are all familiar with the scattering. We always, every day we see the scattering, right? Sky. Right? You see it, right? So I think I will wind up here with showing the light slide. Because this scattering is highly depends on the refractive index, the medium's properties, and most importantly the size of the particles. Okay? If you have we can define my parameter in terms of the wavelength and as well as the particle diameter. Okay? If you don't want to do that, we can simply say, like if the particle size is like less than 10 nanometer, less than 10 times the wavelength of the light, we could typically consider it as Rayleigh particles. And of the order of the wavelength, and then if it is well above, we call geometrical regime. Okay? So different particles, different treatments should be followed. And you can see the intensity from the scattered particle as a function of particle diameter, also as a function of particle m parameter. So that we have to really understand where the particle size looks like. Accordingly, we have to select the desired theory. This is very important. And with that, what we covered is basically we have covered image formation and illumination, interference and diffraction limit, resolution, and I hope special filtering concept it will be useful for you in future if you are working on with the lasers and all and collimators as well, and some basics of cameras. I will be here the whole 3 days, free to mingle. Okay, so basics of polarization and scattering. This also, if you want to have some better understanding about the polarizers in reality, we can have always discussions. Okay. And I recommend you to go through the Fresnel's equations and polarizers to have a better understanding about it.
Okay,
it was well.
Yeah, thank you. Of course, time for some questions, and I don't think we have any further snacks or drinks afterwards.
No, lunch.
So it'll be lunch afterwards. So you can keep them here as long as you want, but you're competing with lunch now. Okay, so. Can we have some questions? I suppose everybody is somehow using optics in the room, otherwise you wouldn't be here. So, and it's not clear to me how much optics they get in their undergraduate and graduate studies, but now is the chance to ask questions. Yep. We started on that.
In Galilean like configuration, we can use plano convex because we are not using that curvature for making for expanding the
Plano
shape.
convex with
And plano concave.
Yeah, you can use it.
Yeah.
There's actually an interesting thing with planned convex lenses. You have your object here and your image here. And the question is, do you put the planar side this way, or do you put the planar side this way? Makes a big difference. And it's actually better to always put the planar side on that side. You get a better image. That's the spherical aberration. But a lot of people don't know that.
Sir, I have a question.
Yeah.
So if we have, let's say we are doing some experiments, microfluidic experiments, so which type of microscope is better, the upright microscope or inverted microscope?
That basically, it all depends on, if you are, the bottom substrate is transparent, you can use
Any of them?
any of them. But if it is not transparent, you have to look from top.
You have to apply.
So, it
Let's say
depends.
if we have both transparent bottom. then-
So it also again depends on the material, right? If if it is fluorescing or if it is like, absorbing particles, so you have to choose accordingly.
I mean, both can be used. Like there is no the preference based on the application, whatever.
So
they
if you want to just to have a shadowgraphy, like you have a high refractive index media and you want to, like droplets, nothing will stop you to use inverted or upright microscope. You should have the proper illumination setup as well as the proper camera to capture.
Further questions?
Can you go to slide number 18?
18.
18.
Yeah.
So sir, here we are expanding the laser beam. So in that case, the intensity value will go down.
Intensity basically will go, definitely per unit area it will decrease because we are expanding the area. That will happen.
So can we contract the laser beam?
Can we?
Can we contract the laser?
You want to reduce the laser? It's possible. You just because physics is, optics is reversibility is applicable. You just put it back so that you can demagnify the beam. Because it's f2 by f1. How you put it will be demagnification. Sometimes we have to do that because we expand and we do optics, but some component may have a smaller aperture. Then we have to demagnify and control and put it. It's possible.
During these cameras, we cannot take pictures from very short distance. Like, can we that issue can be resolved? Like, how can we minimize the focal length?
You have to attach a macro lens to the scenario.
At the same time, the size shouldn't be big, like depending on some application.
Nowadays, cameras lenses coming with a flat as well. because you can make flat lenses as well. Because the lens basically, typically what we discuss is basically the same refractive index and a curvature, right? Same effect, because that's what I told the optical path, right? N into D. Actually what we are varying is D. You can have a variation in N as well, keeping the D constant. That's what we do in optical fibers, parabolic profiles. There we vary the refractive index and bend the beam accordingly. It's possible. Flat lenses are now available.
But they're graded index fibers.
Yeah, graded index. And graded index lenses without any additional component inside the material. Non-linear effects, people do that. Inside the material, just because of the variation in refractive index with respect to the electric field, light will automatically focus.
Nevertheless, these cameras are amazing.
Yeah, this is
The resolution and it's amazing. And by the way, there are now, is this yours? No, this is mine. Now there's even software you can do PIV with you. Commercial, not even commercial, you just download it from the web.
And if you have, we recently developed a long distance dark field microscope for our. So if you have some specific applications, I'm always happy to fun with optics. Be careful, but
Maybe some other, because I know everybody's working with optics, you must have some more questions.
So you explained about the higher resolution, how to achieve the higher resolution, but how to achieve higher frame rate?
higher frame rate is completely electronics part. That's we have no control over it.
So in that case, like the resolution, the frame rates are affecting the resolution as well. So as you showed the
No, the thing is that basically, frame rate basically it is because of the data transfer. If you have a higher frame rate at a high resolution, your computer will die. So you should compromise somewhere. So,
But I could add 2 points to that. One point is, you have a certain bit resolution, so typically 12 or 14 bits, and sometimes at the higher frame rates, the effective bit resolution decreases. So that's not the spatial resolution, that's the bit resolution, the grayscale. And that can actually decrease with high frame rates, but often the manufacturers don't tell you about that. You have to do that on your own and test it. And the other thing about achieving extremely high frame rates, we can go back a few years, and the idea was not to use one camera, but to use several cameras and electronically trigger them, and then you have the higher frame rate. And that's how, when we were doing rocket engines many years ago, before the last technological, we could still get very high frame rates because we were but only 8 or 9 of them. You couldn't, because we had 8 or 9 cameras, so you could go really quick. But typically you want more frames.
Because we work on femtosecond lasers, so when we are capturing the ablation at that rate, so we are not able to capture what is.
So what are you working on?
Femtosecond lasers.
Yeah, okay, that's different. Femtosecond, that's the laser source, not the camera.
Yeah, so we are not able to capture the ablation.
The problem with the femtosecond laser is that they're typically in femtosecond, and any detector, which is a squared law detector, the irradiance, now E1 plus E2 squared, so you're looking at, like your eye is a squared law detector. No detector is fast enough. The typical rise times of even the fastest photomultipliers are maybe 10 nanoseconds. So the problem with femtoseconds is you have to go to autocorrelation to capture what's going on. But okay, this is done nowadays. I mean, we also did a lot with femtoseconds. And that's, I mean, if we talk about temporal resolution, then, and you have a really fast event, think of that shock drop interaction, then there's 2 ways to capture it without blurring, motion blur. Either your illumination is very fast or your shutter speed is very fast. And the illumination you get fast with really fast pulse lasers, like the Cavilux has 10 nanoseconds. When the fast shutter, you actually can never reach that fast. And that the shutter speed is not necessarily the frame rate. It's clearly less than the frame rate, but it's not the same, always. So, yeah, that's a problem. I mean, if you have fast things and you have to freeze them without any motion blur, then you need a fast laser. Yeah. Yeah. Yeah, I can see now we're competing with lunch. Right, let's thank Namboodiri again, and especially because he stays.